Hello, in this video we're going to go over the Lagrange Remainder Theorem. First, I'm going to remind you of a couple of things that I'll be using, and then I will tell you what Lagrange Remainder Theorem is and what is the significance of that, and then we will do some examples. Okay, so one of the things that we proved a while back when we did the Cauchy mean value theorem was that if you have a function under some certain conditions that it has n derivatives and the value of the function and its derivatives all the way to the n minus first derivative are all 0 at a point, then f of x would be equal to fn of z over n factorial times x minus x naught to the power of n for some z between x and x naught. This is one of the theorems. Since we discussed this one a while back, I would like to remind you of that because I will be using that in this video. Second thing is what we discussed last time, which was the nth Taylor polynomial. The nth Taylor polynomial of a function f of x is given by sum of, so this is basically the sum fk of x naught over k factorial times x minus x naught to the power of k, and k ranges from 0 to n. And the only condition for this is our function f must be differentiable n times differentiable. Then this is the unique polynomial that has contact of order at least n with f, and it has degree less than or equal to n, and the contact is at x naught. Okay, so what the reason that we actually discussed these Taylor polynomials is that we wanted to approximate our function f of x by polynomials, because it is easy to deal with polynomials since all polynomials need our multiplication and addition. So ideally we would like this polynomial Pn of x to approximate f of x as n is large. The difference of these two, f of x and Pn of x, is called the nth remainder. So this is the definition. Let I be a neighborhood of x naught. So I'm looking at neighborhoods because I would like to be able to take derivatives. And f from I to r be an n times differentiable function. Let Pn of x be the nth Taylor polynomial of f at x naught. The nth remainder of f at x naught is the function Rn from I to r, defined by Rn of x is f of x minus Pn of x. So it's the difference between f of x and Pn of x. We would like this to go to 0. If Rn of x goes to 0, then we can say f of x can be approximated by Pn of x, and as n goes to infinity, f of x becomes very, very close to Pn of x. This is what we want to prove. Although that's not always true, we're going to come up with some conditions that guarantee the equality. Okay, so first a theorem, very important theorem, Lagrange Remainder Theorem, that we are going to prove, and then we will see some applications of this theorem. So the Lagrange Remainder Theorem tells you that if you look at f of x is equal to the nth Taylor polynomial plus the remainder. And the remainder is equal to fn plus 1 of c over n plus 1 factorial times x minus x naught to the power of n plus 1. So that is what the Lagrange Remainder Theorem tells us. Okay. So just to be precise, this is what it tells us. It tells us let I be a neighborhood of x naught and n be a non-negative integer. Suppose f from I to r has n plus 1 derivatives. Then, so all we need is that we need to have n plus 1 derivatives. We don't need anything about continuity of fn plus 1. Then for each x not equal to x naught in I, there is a point C strictly between x and x naught, such that f of x is equal to the Taylor polynomial plus fn plus 1 of c divided by n plus 1 factorial times x minus x naught to the power of n plus 1. This is actually relatively easy to prove. And the way we're going to prove that is by using the theorem that I just reminded you. So let Rn of x be f of x minus Pn of x, where Pn of x is just that Taylor polynomial. x minus x naught to the power of k. K ranges from 0 to n. So what we know by a theorem, if you take Rn of x naught and take the kth derivative, this is fk of x naught minus Pn k of x naught. This is just by additivity or linearity of derivatives. Now, fk of x naught and Pnk of x naught are the same. So this is 0 for k from 0 to n. And this is where I'm using the theorem. So the theorem was f of x and Pn of x have contact of order at least n. So this Rn of Rnk of x naught is 0. So now I can use the above theorem that I stated, and this was so if you go back to this one, the condition was you need the function and its derivatives to be all 0. 5.13. So by theorem 5.13, Rn of x is going to be equal to fn plus 1 of c divided by, or Rn plus 1 of c divided by n plus 1 factorial times x minus x naught to the power of n plus 1. So this is the theorem. However, if you look at Rn plus the n plus first derivative of Rn at c, this is equal to n plus first derivative of f at c minus Pn at c, the n plus first derivative of Pn at c. But this is equal to 0. This one is 0. So this is fn plus 1 of c. Since degree of Pn is less than n plus 1. Since it's a polynomial of degree less than n plus 1, n plus first derivative is going to be 0. And therefore, Rn of x is fn plus 1, the n plus first derivative of f at c divided by n plus 1 factorial times x minus x naught to the power of n plus 1. Now, we are going to substitute Rn by f of x minus Pn of x. So that's equal to, and by the way, this is for some c by the theorem. This c was strictly between x naught and x. Okay. So this is equal to fn plus 1 of c over n plus 1 factorial times x minus x naught to the power of n plus 1. So all I need to do is to move Pn to the other side, and I get exactly what I wanted. Okay. So of course that's exactly what I wanted, because Pn of x is the nth Taylor polynomial that I had in the statement of the theorem. Okay. So let's use this one to prove something on the face value unrelated. We want to show that E is irrational. So this is an interesting application. So it seems like this might not be even related to, like, how do you even show irrationality of E using advanced calculus. But this is an interesting application. So here's what we're going to do. We're going to apply the previous theorem, the Lagrange Remainder Theorem, to the polynomial P of x. So by the Lagrange Remainder Theorem, for every x not equal to 0, there is some c strictly between x and 0, such that e to the x is equal to the nth Taylor polynomial of e to the x, which is the sum x to the n over n factorial x to the, I guess, k over k factorial, k ranges from 0 to n, plus the n plus first derivative, which is e to the x also, so evaluated at c, divided by n plus 1 factorial times x minus 0 to the power of n plus 1. So this is the equality that I get. Now I'm going to substitute x by 1. So replace x by 1. You're going to get e equals the sum 1 over k factorial plus, and this k again goes from 0 to n, e to the c. We don't know what c is. We just know that c is between 0 and 1. And this is for some c between 0 and 1. Okay, what we want to do is we want to show that e is in fact irrational. How do we show irrational? How do we show something is irrational? Being irrational means it is not rational, and proving negatives is often done by proof by contradiction. So let's in fact apply proof by contradiction. So on the contrary, assume e is rational. So that tells us e is equal to sum a over b for some positive integers a and b. Okay, because it's a rational number, it's integer over integer, positive integer over positive integer. Now, take this expression and multiply both sides, this expression that I have up here, multiply both sides by n factorial. So n factorial times a over b equals the sum n factorial over k factorial, k equals 0 to n, plus e to the c over n plus 1. Now, if you look at this expression is an integer. So note that n factorial over k factorial is an integer for k equals 0 to n. I can also make n factorial over n factorial times a over b an integer. If n is at least b, then n factorial a over b must also be an integer, because if n is larger than b or at least b, then the denominator is going to be cancelled with n, with the n factorial, because there's going to be some b in the product of 1 through n. So thus, if n is at least b, we know this is an integer, we know this is an integer, the difference of two integers must be an integer. So that means if n is greater than or equal to b, then e to the c over n plus 1 must be an integer. Now, note that e to the c over n plus 1 is positive, and it's also less than, because c is less than 1, we don't know what c is, and c actually depends on n, but whatever it is, it would be less than 1. Now, if n is more than e minus 1 and greater than or equal to b, then e over n plus 1 would be between 0 and 1, and e over n plus 1 is an integer. So if n is at least b, then e over e to the c over n plus 1. So let me be a little bit more careful here. So what I get is, if n is more than e minus 1, then e over n plus 1 is going to be less than 1. And that means e to the c over n plus 1 is going to be between 0 and 1. So that means e to the c over n plus 1 cannot be an integer. And this is a contradiction. Therefore, E must be irrational because we assumed E is rational and we obtained a contradiction. Okay, so what we did was we showed that e to the c over n plus 1 must be integer by clearing the denominators, and then we showed that e to the c over n plus 1 can be actually less than 1 when n is large. Okay, so this is an interesting application of what we discussed. So we proved the Lagrange Remainder Theorem, and then we used it in a seemingly unrelated topic, which is E is irrational. Now, we would like to talk about when this function f can be approximated by Pn. In other words, when is it that Pn approaches f of x as n goes to infinity? So for that, I would need a little bit of preparation. And this is something that we will need for the rest of the course. We will talk about these series extensively. Given a sequence of real numbers a n with n greater than or equal to 0, the sequence Sn defined by the sum from 0 to n of ak is called the sequence of partial sums of this series. The number ak is called the kth term of this series, and Sn is called the nth partial sum. If Sn's converge, then we say the series converges, and we say the sum is equal to the limit of those partial sums. If Sn diverges, then we say the series diverges. Okay, so let's now, given that, let's prove the theorem. So if we want to prove that the Taylor polynomials approach the function, we will have to show the difference is 0, approaches 0. Okay, so let I be a neighborhood of a real number x0, and assume f from I to r has derivatives of all orders. Suppose r and m are positive numbers for which x0, x0 minus r to x0 plus r, that interval, closed interval, is inside r, inside I, and if n of x doesn't grow too rapidly. So it is, I would say, I would call it sub-exponential. So it is less than or equal to some exponential. Then f of x is equal to the Taylor series. Okay, so how do we prove this equality? So f of x is equal to this sum n equals 0 to infinity fn of x0 over n factorial times x minus x0 to the power of n. If and only if f of x is equal to the limit as n approaches infinity, this sum is, this infinite sum, this series, is the limit of the partial sums. And partial sums are exactly the Taylor polynomials, where Pn of x is the nth Taylor polynomial of f at x0. Okay, so this equality holds if and only if, so f of x is equal to the limit as n approaches infinity of Pn of x, if and only if the limit of f of x minus Pn of x is 0 as n approaches infinity. And this is pretty straightforward by properties of limit. If you have this one, then you just subtract f of x and you get this. If you have this one, then you just subtract f of x again and multiply by a negative sign. Now let's look at f of x minus Pn of x. By the Lagrange Remainder Theorem, there is some number, let's call it maybe Zn, strictly because it does depend on n, I'm going to call it Zn. Strictly between x and x naught, such that f of x is equal to Pn of x plus the remainder, which is fn plus 1 of Zn over n plus 1 factorial times x minus x naught to the power of n plus 1. Okay, so, and by the way, this is for x inside that interval, so it is the same x that they talked about in the problem. Okay, now in order to show the difference is approaching 0, limit of f of x minus Pn of x is 0 as n approaches infinity, if and only if limit of this fraction fn plus 1 Zn over n plus 1 factorial times x minus x naught to the power of n plus 1 is 0 as n approaches infinity. So we need to show that this quantity approaches 0. This is what we want to show, it approaches 0. Okay, one thing we know about this function, and it is the fact that nth derivatives do not grow too fast. This is an important part of it that we're going to use. So now, by assumption, fn plus 1 of Zn is at most m to the power of n plus 1. Also, since x is inside the interval from x naught minus r to x naught plus r, we have the difference between x and x naught is not more than r. So this means that fraction fn plus 1 of Zn over n plus 1 factorial x minus x naught to the power of n plus 1 is less than or equal to m to the power of n plus 1 r to the power of n plus 1 divided by n plus 1 factorial, which is mr to the power of n plus 1 over n plus 1 factorial. Okay, if I show that the right hand side approaches 0, then I would be done. Then this would be 0 by the comparison lemma. So if we show limit of mr to the power of n plus 1 over n plus 1 factorial is 0 as n approaches infinity, by the comparison lemma, limit as n approaches infinity of fn plus 1 of Zn over n plus 1 factorial times x minus x naught to the power of n plus 1 would also be 0 as desired, and then we would be done. So all I need to do is to show that this fraction mr to the power of n plus 1 over n plus 1 factorial in fact does approach 0. And we will do so by the ratio lemma for sequences. We will show this sequence Cn equals mr, and by the way, this mr is just a constant. It doesn't matter what constant it is. This approaches 0 by the ratio lemma for sequences. Okay, how do we do that? Ratio lemma for sequences was you take the sequence and you take the ratio of the consecutive terms, so Cn plus 1 over Cn, and then you take the absolute value. This would be mr to the power of n plus 2 over n plus 2 factorial multiplied by n plus 1 factorial over mr to the power of n plus 1, and that's mr over n plus 2. Mr is a constant, and 1 over n plus 2 approaches 0 because 1 over n approaches 0. So thus, by the ratio lemma for sequences, limit of Cn is in fact 0 as n approaches infinity. As soon as we show Cn, which is this, approaches 0, this guy would also approach 0, which means the remainder approaches 0, which means the limit of Pn is equal to f. So this is one condition that if we can prove that fn of x, the nth derivative of f, doesn't grow too fast, then we can show f of x is equal to its Taylor series. Okay, so now that we have settled that, we will do a couple of examples. One thing to keep in mind is that this theorem doesn't tell you the converse is true. In fact, the converse isn't true. What the theorem tells you is if you have this condition, then you can write down f of x as its Taylor series, if f of x is equal to its Taylor series. But it is possible for this inequality to not hold, and still you would have this equality. In fact, there are examples of that. I will talk about that in a few minutes. Okay, but first let's do one example on this. So we want to prove that for every real number x, we have e to the x is equal to that. So what we want to do, I want to show that this function satisfies the conditions of the theorem. So let r be positive and consider the function f of x equals e to the x. Now, if you look at fn of x, fn of x is just e to the power of x. All of the derivatives of f are e to the power of x. E to the power of x is at most e to the power of r for all x inside negative r to r. So I know that. And what I need is fn of x. I want it to be less than or equal to m to the n. This is just m. So can I say this is less than or equal to e to the power of r to the power of n? Yes. This is because e to the r is at least 1. Or in fact, it is more than 1. Because r is positive, e to the r is more than e to the 0, which is 1. So thus, f satisfies the conditions of the theorem that we just proved, 8.4. with m equals e to the r. Therefore, f of x is equal to the sum xn over n factorial n equals 0 to infinity. We have shown that the Taylor polynomial of f of x is the sum of x to the k over k factorial from 0 to n. So this is something we have done before. Therefore, we have this equality, but this is only true for all x between negative r and r. So what we need to show is that in fact this function is equal to this Taylor series for every x in R. And why can we do that? Because for every x there's an R more than that. So since the union of negative, let's say negative m to m from m equals 1 to infinity gives you the entire real line, every x belongs to some negative m to m. Thus, e to the x is equal to the sum x to the n over n factorial, n equals 0 to infinity. Yeah, I guess I could just say this. I could just say, since every x belongs to this, Yeah, this would be just easier. So every x belongs to some negative m to m. For example, when m is absolute value of x. So since we have this, we have f of x is equal to that Taylor series. And that's exactly what we wanted to show. So this is for all x, for all real numbers. So therefore, e to the power of x is equal to its Taylor series. So this was an example of a function that satisfies the conditions of the theorem. Okay, now let's look at another example. This is in fact an example of a function that shows the weakness of not only the previous theorem, which was the result of the Lagrange Remainder Theorem, but it also shows the weakness of the Lagrange Remainder Theorem itself. Lagrange Remainder Theorem tells you a function, if you start from a function, it's equal to its Taylor polynomial, and then it gives you an estimate, it gives you a formula for the remainder. And this is the formula that we discussed earlier. Here. So this is the remainder. It gives you a formula for the remainder. However, in the formula there is a c, and we don't know exactly what that c is. So not knowing what c is, in fact, makes it sometimes difficult to deal with this formula. And I will illustrate that with this example. This is a very good example. So let's take f of x to be natural log of 1 plus x. Okay, so let's see what the question says. It says, for what values of x can you prove the Taylor series of natural log of 1 plus x at 0 converges to natural log of 1 plus x? Let's try and see for what values we can do that. Okay, first of all, if we look at the nth derivative of that, and this is something we did a couple videos ago. So we have that fn of x is equal to, I believe it was negative 1 to the power of n plus 1, n minus 1 factorial, 1 plus x to the power of negative n. I believe that was the nth derivative of this function. Now, I would like to see if I can show, in fact, this fn. I can either use the Lagrange Remainder Theorem, or I can use the theorem that followed from Lagrange Remainder Theorem. So of course, since the theorem followed from the Lagrange Remainder Theorem, it would be better to just use the Lagrange Remainder Theorem. We would get something stronger, hopefully. So by the Lagrange Remainder Theorem, what we get is this. F of x is equal to Pn of x plus Fn plus 1 of c over n plus 1 factorial times x to the power of n plus 1 for some c strictly between 0 and x. So we know that. Okay, and in order to show that, in fact, so we know limit of Pn of x by what we just showed above as n approaches infinity is equal to f of x if and only if limit of fn plus 1 of c, which I'm going to call that perhaps cn over n plus 1 factorial x to the power of n plus 1 as n approaches infinity is equal to 0. So if I show that this approaches 0, then limit of Pn would be f of x, which means f of x is equal to its Taylor series, and vice versa. Okay, so under what conditions is this going to 0? Let's now evaluate this. We know what that is exactly. Fn plus 1 is, so this is if and only if the limit as n approaches infinity. Fn plus 1 is negative 1 to the power of n plus 2 n factorial times 1 plus x, or 1 plus cn to the power of n minus 1, if we just look at the formula that we have, divided by n plus 1 factorial times x to the power of n plus 1 is 0. If and only if the limit as n approaches infinity, negative 1 to the power of n plus 2 over n plus 1, n factorial and n plus 1 factorial cancel to n plus 1 at the bottom, and then we get x over 1 plus cn to the power of n plus 1 equals 0. Okay, so in order to show that this fraction approaches 0, what I need to do is to know that is to show that this quantity is in fact less than 1. So we need, because if x over 1 plus cn to the power of n plus 1 is more than 1, and recall that we don't know exactly what cn is. All we know is that cn ranges between 0 and x. That's all we know about cn. So if we were to show that this actually approaches 0, we need the exponential to grow slower than n plus 1, and that could only happen if that exponential is just something less than or equal to 1 to the power of n plus 1. So we need absolute value of x over 1 plus cn to be less than or equal to 1. For every c, I'm going to call that c now, because again we don't have any information about cn. All we know is that it is between 0 and x. So for every c between 0 and x, we need this inequality. Now if you look at this fraction, the denominator is 1 plus c, so it's a linear function. So if you look at 1 plus c, 1 plus c is between, all we know is it between 1 and 1 plus x. Thus absolute value of 1 plus c is between 0 and maximum of these two, 1 and 1 plus x. Absolute value of 1 plus x. So in other words, if you want to find the largest of absolute value of 1 plus c, what you need to do, and smallest of that, what you need to do is you need to look at the endpoints. So we need this. We need x over 1 plus 0 to be less than or equal to 1, and we also need x over 1 plus x to be less than or equal to 1. These are the two things that we need. Let's work on both of them and see what they give us. If you look at the first one, we get x is between -1 and 1, and the second one gives us x over 1 plus x is between -1 and 1. Let's work on the left side of this. So that gives you 0 less than or equal to, so I'm looking at this one, 0 less than or equal to 1 plus 2x over 1 plus x, and the right side gives us minus 1 over 1 plus x is less than or equal to 0. So that means 1 plus x must be positive. From this one, we obtain that 1 plus x must be positive, and 1 plus 2x must be greater than or equal to 0, because the denominator now is positive. Therefore, for this one, the denominator is positive, therefore the numerator must be non-negative. And this tells us x must be greater than -1 and x is greater than or equal to -1/2. And we also know x is between -1 and -1 and 1. So thus, these are the conditions that we need. X is between -1 and 1, and x is greater than -1, and x is greater than or equal to -1. So this means x must be anywhere from -1/2 to 1. So ln of 1 plus x is equal to its Taylor series for all x inside -1/2 to 1. Okay, everything else we don't really have any information about. However, it turns out that ln of 1 plus x is in fact equal to its Taylor series for every x from -1 to 1. So in fact it is true that the equality holds not only from -1/2 to 1, but it holds from open -1 all the way to 1. It doesn't hold for anything else, but it does hold for that. So this shows you that even though the Lagrange Remainder Theorem does give us some understanding of the remainder, it is not the complete picture. It tells us something about the remainder, but it doesn't give us the full picture, which means we will need to have some better tools to understand the picture. And this is something we will address in the future videos. Okay, so this brings me to the end of this video. So if you would like to continue with this topic of advanced calculus, feel free to subscribe, and I will see you in the next video.